the Sunday webinar series. I hope you are having a good Sunday morning, and thank you so much for everyone for joining this session. Today is a very interesting topic. I have been looking into analytics for the past 18 plus years, and one of the things which I have specifically experienced basis working with analytics and AI. There was one saying somebody said that success is not solely analytics. It's easily available data, easily accessible data, and then the various concepts around how this data is actually engineered. So today's topic is very interesting and very close to my heart, which is around the demystifying data engineering. And there we will be specifically focusing on a few specific sections. One will be around what are the basics of data engineering? What are the nuts and bolts around data engineering? The second thing will be more around just giving some detail around uh, the architectural choices which we have, the various options, the plethora of options which we have right now from a data engineering perspective. We will also be talking about the processing options, the data storage options, and all those things. The last specific thing, but the most important one, we understand that there are a lot of students, there are working professionals. Some of them actually want to make their career in data engineering. So, what does that mean? How do you make a successful data engineering career? That is something which we'll be covering. So today we have two special guests uh, who are experts in this area. We have Hindol Basu. Hindol actually is the CEO of Actify Labs. He brings in 19 plus years of experience, specifically in the machine learning, in the different industry verticals. He has worked in different industry verticals. He has led multiple analytics initiatives in India, Asia Pacific, and North America, and has worked in wide variety of industries, including financial services, manufacturing, forth. He has also developed innovative frameworks, solution frameworks in IoT, leveraging the specific set of the machine frameworks, and so on and so forth. So I can speak about Hindol a lot, but I would also give him time just to give a brief introduction about himself. And then we also have Bijoy Khandelwal, who is the co-founder and COO, Chief Operating Officer of Actify. And Bijoy actually brings in a wealth of experience from a perspective of product and engineering, from working on different specific frameworks, whether it's around Java, J2E, Spring, or around the different components around machine learning. And from a data engineering perspective, he brings a wealth of experience in terms of advising a lot of clients around what is the best choices from a data engineering perspective. So without further ado, I will hand over the mic to Hindol. Hindol, welcome. Bijoy, welcome. Thank you so much for giving time on this Sunday. And all over to you.
Thank you, Kapil. Thank you so much. Thank you, Kapil. Thank you, NK. As always, it's a pleasure to be part of the 3AI initiative. It's an honor and privilege to be there. Thank you so much. So as Kapil mentioned, we will go through some of the architectural details around data engineering, some of the basics of data engineering, then some of the choices about how do you store data, how do you process data, and then some bit of tips or suggestions from older people like us to young professionals, so that whatever little we have learned through these many, many years of our hairs becoming gray, we can share it to the advantage of some of the young professionals on the forum. Okay. So we will just share our screen. Bijoy, can you share your screen? Okay. And as we go along, I'm sure that there will be lots of questions. We will have about maybe 15 minutes at the end of the session to discuss questions. Please do ask lots and lots and lots of questions to us. So the first part of this presentation, in the first 5 or 6 slides, I will try to explain the concepts behind data engineering, what is involved in data engineering, and what are the things that one has to keep in mind if one is creating a data engineering architecture for a specific use case. So we will start from very simple. So if you can see, all data engineering can be looked as pipelines. So as you see in our pipeline water flows, similarly, a data engineering is nothing but creation of this complex or simple set of pipelines or plumbings through which data flows. So in any organization, as we know, data is pretty much the heart of AI and machine learning. Without data, AI and machine learning just doesn't exist. So therefore, we have to move various types of data, and we have to process various types of data to create AI and to implement AI. So data engineering is essentially the plumbing or the pipelines to move and process data so that we can get the right data to build our AI solution and to implement our AI solution. So as you can see in this diagram, what we have is, you can almost think of it as a set of pipelines through which data is flowing, and there are various operations which happen on the data. Now, the source of the data can be various. It can be from data storage, like a data lake or a data warehouse. It could be from an app. It could be from a machine which is producing sensor data. It could be captured by the human being. So it could be any. The usage or the operations on the data can be various. And again, there are various use cases of data. So essentially, all data engineering can be looked at creating the right plumbing through which data flows. So we'll go to the next slide. So what are the aspects which determine how we will design our data pipelines or our data engineering? So as you could see, there are 3 elements involved in it. One is, all data is produced somewhere, right? Data is produced in an organization somewhere. So it can be a CRM system, it can be an app, it can be a machine, it can be a human being entering data. There is somewhere data is produced. So we need to understand what are the ways in which data is produced, and the way that data is produced has an implication of how we create our data engineering design. Then once the data is produced, the data is used by someone, which we call it data consumers. For example, it can be used by a website to show how many products a customer has. It can be used by a call center. It can be used by an analyst or a data scientist who is building a machine learning model. It can be used for implementing a machine learning model. So there can be various data consumers. And then this data itself may have various characteristics. It can be structured, it can be unstructured, it can be semi-structured, it can be data which is coming very fast, or it can be slow moving data. So it can have various characteristics. So the type of data engineering architecture that is best suited depends on the characteristics of the producer, the consumer, and the data. So we will quickly go through each one of this. Now, for example, if you look at data producers, who are data producers? All business processes in an organization produce data. Now, if you look at all the ways in which data can be produced in an organization, these are the 5 most generic ways in which data can be produced. The first is streaming producer. I mean, data is produced almost instantly, like an app. Whenever someone is going, clicking, moving around, or whenever in a website someone is going, clicking, moving around, data is being produced instantly. Then there is batch data producer. Data is not produced real time, but it comes in bursts. Like when a customer joins, you get a set of information about the customer. When a new supplier is registered, you get a set of information. So it can be batch, which is a predetermined batch, which is maybe every end of month, some things happen and some data is produced, which is a predetermined batch, or the batch can come anytime. When a new supplier joins, a handful of data is produced. There's another, which is data may be generated by the human hand. Now, whenever we look at data, one aspect which is very important is the aspect of what is the correctness and reliability of the data. So whenever you have data which is produced by the human hand, maybe data which is entered by someone, or data which is captured from a user, there are chances of data quality issues. So we need to understand cases where data is produced by human hands versus when data is produced by a machine. So which is data produced by a machine could be streaming data, which is like machines in factories, etc. Or it may not be streaming, it may be batch, but it is still produced by a machine. And data produced by machines are usually more accurate than data produced or entered by the human being.
Yeah, Hindol, sorry to interrupt. We lost your video for some reason.
You lost the video.
Yeah.
You're able to hear me, right?
Yeah, I can hear you. We can hear you. I don't know if only me, I'm not able to see the video. NK, are you able to see the video?
No, Kapil, we don't see the video. Audio is clear.
Yeah.
Okay, now we can see.
Now you're able to see? Okay,
Yeah.
okay.
Let's continue.
Let's continue. Okay. Bijoy, can you go to the next slide, please? Okay. Now, the next is how we consume data. Now, sometimes you may consume data very fast in real time, which is the data is produced every 1 second and the data is consumed every 1 second also. It can be what we call is near real time, meaning the data is consumed not instantly, not every second, but still maybe every 5 minutes, every 2 minutes, but still relatively faster. Then there is a batch. Maybe it is consumed every end of month, every end of day. Now, for example, maybe a credit card company generates a set of information at the end of every billing cycle for a customer. So it can be batch. It can be ad hoc at any point in time. For example, you want to build an analytical model. You just want to get a large set of data to building your model. So therefore, some data is stored in what we call is hot storage, from where I can retrieve the data immediately. Sometimes it's stored in cold storage, where it may take me a lot of time to retrieve the data, which is okay. Now, for example, if I have to implement a machine learning model, I need hot storage because I need the data right now. But if I have to get some data for performing some analysis, it's okay even if I take a day to get all the data for me to perform the analysis. So that involves a cold storage. Bijoy, if we go on. The last piece which dictates how we will create our engineering architecture is the type of data. Of course, all of you know about structured and unstructured data, which is for all unstructured data, we need to do some engineering on top of the data to make it structured so that we can use it. The other aspect is the size of data. Of course, again, all of you have heard about big data and Hadoop, etc. Now, if you have massive data, now big data comes, or when you have massive data, you may just sometimes want to store massive data. You may not be using massive data for processing. So how much or what is the size of the data that you are using for storage and how much you are using for processing? You may be having data of maybe 1 trillion transactions from history to date. But for a particular processing, you may be using only 1 GB of data, which is last 1 month of data. So storage versus processing, there is a difference. So large data doesn't necessarily mean that if we are storing large data, we will always be processing large data. The other is the velocity of the data. For instance, we spoke about data which is streaming, meaning data which is coming very frequently. That is another characteristics of the data which dictates how we will create our engineering architecture. So these are the 3 components which determine how we will create our architecture. Now I'll hand over to Bijoy to talk about how we will create
No. Hello.
Yeah, Bijoy, we can hear you.
Yeah, I think we lost him, dog.
I think the last he was mentioning is that he wanted to hand over the mic to you,
Oh,
Bijoy.
okay. Oh, okay. Okay. Cool. So I'm audible, right?
Yeah, Hindol, you're audible now. Yeah.
No, this is.
Yeah, yeah,
Oh,
Bijoy, you are
Bijoy.
audible. You are audible. Go ahead.
Yeah.
Okay. 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 Cool. So after understanding the actors that play a significant role in deciding the data pipeline that we create, or the actors that affect a lot what kind of pipeline we build. I'll just focus on few components of data pipeline or data engineering as such. The first one that we do is ingestion. That whenever you have different systems and you want to ingest it to a common platform, because the most important problem to be solved is bringing data uh, to a common platform to process, whether it is a warehouse, data lake, or a data lake, whatever, or an analytical tool, whatever it is. The first thing is ingestion, and the various ingestion technology or techniques that are available are a normal JDBC connection that can be made on a RDBMS system. Flume or Kafka, or Kinesis, if we are talking about real-time streaming of data from a source, or RabbitMQ or Niffy, if we are talking about real-time, but not maybe parallel ingestion of streams. The next one is processing. That once you ingest the data, the kind of processing that you require to transform the data and apply your use case, maybe an analytical model, or just aggregating data to a level. You can do it by a normal programming language using Java, Python, or if you are trying to process real-time streams, you may use Spark. Sometimes for batch processing, if you have a lot of data that you want to process for making a model, you may also go for a batch processing like MapReduce. So these are some of the alternatives available. For storage, again, it can be a normal NFS, a file storage, a RDBMS, more likely, or if you have a use case, we go for SDFS, other NoSQL databases where we can store data. So these are some of the options available for storage. And last but not the least, that all this ingestion, processing, storage, in this times, we don't think about manual processing or manual ingestion or manual storage of stuff. We always look at automating the flows. Should not be any human intervention, as Hindol talked about in the first slide. So we have automation workflows or workflow orchestration tools. And then again, when I talk about tools, it's all open source, not talking about anything proprietary. Apache Airflow, Uzi, Azkaban, which come from LinkedIn, or just normal cron jobs, to be very simple. You make your workflows where it ingests data, process it, stores it for consumption, and the whole process is automated by a workflow so that there is no intervention, manual intervention required. So these are some of the components when you think about building a data pipeline. Now, before I move to the architecture and what kind of stuff we should use to create our pipeline, it's the most important thing that I always talk about. It's the world of technology is filled of tools, filled of stuff that you can use for ingestion, processing, and transformation or storage. If you look at ingestion, you have Kinesis, just for streams. If you look at streams, you have Kafka, you have Flume, you have Niffy, you have Kinesis. So a lot of them. So most of the people get stuck in what to use. What I say is it's more important that you know what you should not use. And that's what affects the most. For example, I've given some of the examples that if you have an application and you have a communication within the modules inside an application, I'll never go for Kafka. It's a overkill. If the size and frequency of data, if it's not huge, even if it is streaming data, but the size and frequency is not huge, I can do it with a normal messaging queue. Why to go for Kafka? Because Kafka is mostly used for high frequency, huge data, parallel processing, all those kind of stuff. So I'll not go for Kafka, for example, when I'm talking about streaming data. Second, nowadays people have this fantasy of going towards NoSQL only for the sake of using a NoSQL. So giving just an example of Uber, they moved from a SQL database to another SQL database after at least 3 to 4 years of research over how to move from SQL to NoSQL. We have to accept that, yes, SQL is easier to handle than NoSQL. So until and unless you have a use case that compels you to move to NoSQL, there's no pride in moving to NoSQL. It may be a foolish step. Again, a very common saying that Hadoop runs on commodity hardware. Again, I've given just pieces of statements that normally revolves around the market. The Hadoop runs on commodity hardware. Your laptop, 8 GB or 16 GB, is not a commodity hardware. They are not talking about it. They're not talking about desktops. The meaning is you don't need specialized IBM big machines kind of systems to run Hadoop, but yes, you need a decent sized server to run Hadoop. It's not your laptop. You can't run production on your laptop. So that's not a correct statement. Spark is fast because it runs on memory. Again, no big deal about it. People from last 20 years know that whatever you run on memory will be fast. So there's nothing big about it. If you need that kind of processing, if you need that kind of speed, Spark is good for you, or a simple Java program or Python program can do your job. So no point in moving to Spark investing memory. Memory doesn't come for free. It's costlier than your disk. So think about it before you move to that. You are writing few records to your database. No, you don't need Spark. And again, as I told about SQL and NoSQL, you have to understand that there's no pride in using MongoDB and Cassandra. If your work can be done by a simple MySQL query, you're good to go. There's no point in going to MongoDB, Cassandra, HBase just for the sake of using a NoSQL. So these are some of the points. I've not listed all, but some of the points that will help you to start simple, move simple, until unless you are compelled or forced to use something complex. Or your use case doesn't force you, rather. Next, as Hindol was talking about batch data, real-time data, I'll just give an example or an engineering way of making a batch data processing framework. So for batch data processing, again, these are source systems which does not need real-time decisioning. If they come in batch mode, when I say batch mode, it can be every 1 hour, it can be every 6 hours, it can be end of day, once in a day. So these kind of frameworks for this kind of architecture is well suited for use cases where you don't need real-time decision. You have an extract point. If you see on the left-hand side, now these are sources, which can be varied sources, SQL, NoSQL, files, ad hoc files, where you put an extract mechanism or connectors. Now again, these connectors may not be Flume or Spark. It can be just a Java developed connector or a Python developed connector based on JDBC or ODBC protocol, a simple 6 lines of code, which can extract data from these source systems in a batch way. Again, you have a transform where you transform the data, filter, aggregate, whatever your use case is in, at what level you need the data to reside. You load it to your data warehouse or a data lake or a delta lake for saying sake. And then You use it for your analytics or for reporting, dashboards. These are usually, as I said, day-in jobs, not real-time jobs. The good part is, and again, if I go by the market, this won't be really appreciated because people are more towards real-time decisioning. But no, it's not always the case. If you and I'll give an example. If a management wants to see a dashboard only once in the morning, there's no point in refreshing it every 1 minute or every 5 minutes and wasting resource on that. Because these kind of process which runs batch, they run on disk. They don't run on memory. So it saves you cost. Unnecessary expenses are not there because you're not spending on memory, you're just spending on disk. These are low cost pipeline, takes longer time. But anyway, you have to run the job overnight and see the result in the morning. So it doesn't hurt you. The only thing is these are not made for real-time insights. But yes, there are use cases where you have to use batch data processing to save cost, actually to use it optimally. Now the use case, as I was telling for batch data processing, that if you see this use case that an insurance company stores its data in 3 different systems. One is Microsoft SQL Server, claims data in PostgreSQL, and a client's demographics data in Oracle. So again, you have this JDBC connectors to all these 3 sources. And the CEO wants to look at the dashboard that needs data from all 3 sources. And he wants to see it every morning. So these kind of use cases where the data is used only once or maybe twice, or maybe the frequency is very low, you may not want to go for a real-time streaming and real-time processing, thus saving cost and also providing the output effectively. So this is, as I told, a low cost but effective way of processing data, depending on the use case. The next one is the real-time streaming. Again, if you see, the actors in the architecture remains the same. You have a extract way, you have a transformation layer, you have a storage layer, and then you have your consumption downstream systems who consume. So it's same as batch processing. What changes? What changes is the technique to do that. You have source systems which are producing events or streams. If I take an example, maybe a temperature sensor or maybe Twitter feeds. So it's feeding almost every second or less than a second. For that, just to make it simple, there is no difference. You have to extract the data as you did in batch processing. What changes is here you cannot have a normal JDBC connector to just pull data. We have replaced it by something like Kafka. Again, it's not de facto. There are a lot of stuff. There is Kinesis and stuff, RabbitMQ, which you can use. Kafka has replaced the JDBC or ODBC protocol so that the data can be fetched as streams rather than batches. Suppose streaming of data. Again, for the processing layer, we have put Spark. Again, it can be something else. It can be Storm. So Spark is used for real-time streaming. Again, it uses memory. So it's fast. It has the capability to receive stream, process it within seconds or milliseconds, and push it to data storage. Now, on the storage part, again, you can use a storage which has faster output, can be queried faster, maybe an Elasticsearch or maybe an HBase, on which ACID kind of transaction is possible. And the dashboards or the real-time decisioning that comes out of it, it comes in seconds or milliseconds, because if you see the actors in this whole architecture, they all are tuned to process streams so that real-time decisioning is possible. Now, some of the things with this kind of architecture, as I told, I'll just reiterate over that. The process usually runs on memory so that it is faster. And because of that, the cost is high, because of the basic bottom line is memory is far more costlier than disk. So that is why only when real-time decisioning is really needed is when we go for such kind of architecture. Again, There's no pride in using real-time streaming when you don't need it. So, example, a vehicle insurance company wants to give discount to its customer on their driving behavior. Better driver gets better discount. For this, they track the driving behavior of the drivers with OBD device. So these are devices normally which we can plug it into your car and it gives real-time info about how you drive and what's the condition of the car. The company wants to store the driving data in the storage part for taking out a driver's score on basis of which they'll give discount. And also, so this is important, and also wants to send real-time alerts to the drivers. So one part is storing the data so that it can be used for some analytical model building. But one part of it is also real-time insights, that is real-time alerts to the driver if they're driving rash. So if you see, the OBD device pushes data to Kafka, and Kafka pushes data to two sites. One is to the storage. Now this storage will be used for building a model to take out the driver score. On the other side, it also pushes data to Spark so that real-time and analysis can be done. And if there's a rash driving alert, that alert can be pushed to the driver real-time. The moment he makes a mistake, within milliseconds or seconds, he gets that alert. So one part is storing, but we'll focus on the real-time alert because that is what I wanted to show you. That if you're looking for real-time insights, this is the architecture to go. Again, the components, Kafka, Spark, this may change, but this normally remains the architecture. Now this is one again. When I tell a company or an organization normally doesn't decide that we are a real-time streaming organization or we are a batch processing organization in our IT plan or IT perspective. No, it doesn't happen that way. In reality, it's always a combination of real-time and batch processing, which takes a organization ahead in terms of data and data processing. So this is about it's one of our platform, the Actify. So I'll focus more on the architecture of it. If you see, and I'll run through a bit quick because it's complex. If you see the first on the left hand side, there is an IoT gateway which process or streams data from streaming sources like a smart meter, or as I told, a temperature sensor or an air quality sensor. It streams data from those sources, pushes it to an IoT gateway. Again, IoT gateway is an intermediate channel which helps in processing or collecting data from different sources, different streaming sources. It pushes the data to the producer, which is again, the producer and the consumer is a part of a messaging queue or a message broker. So collectively, you can take it as Kafka because it happens inside that. Kafka, Kinesis, RabbitMQ, all those kind of technology. From there, the data goes to two places. On the top, if you see, it goes to Spark processing engine, so that which has the capability of processing it real time. And after that, it is pushed to a streaming dashboard, the dashboard which has a use case of refreshing maybe every second or whenever data comes in. It has a real-time use case. And the other part goes to your data lake, maybe a data lake or a delta lake or a data warehouse, whatever storage strategy you have as an organization. It has a data quality layer, a drag and drop workflow component. As I told, you need a workflow orchestration tool to automate the whole flow. You cannot have manual intervention. So once the data goes to the data lake, so there are two outputs. One is the streaming dashboard, which again gets viewed by the user. The other part is the data lake. It goes to the data lake, which is a repository of all kind of data, whether it is batch or streaming. On the data lake, you have a data quality layer, drag and drop workflows components, which helps you transform the data using a visual tool. Again, no rocket science, you do it by code. Here it is visual for even business people to use it. But finally, on the architecture front, transforming the data and then pushing it to data marts. This is nothing but a concept of data warehouse, which in the modern era has been broken down into data marts. So earlier, you used to have a single data warehouse structure, a star schema, where for any kind of, which is again transformed, any kind of use case, you hit your data warehouse and get it because it has all kind of data. But in the modern era, and again, there are benefits on that, which we may discuss later, not now. But the whole warehouse is broken into smaller data marts. Again, each data marts cater to different use case. One data mart or 3 or 4 data mart, as you see in the diagram, may fuel your dashboards, which are either near real time or batch. Few of the data marts you can use for your machine learning and AI consumption layer, or any other data push kind of stuff that you have. Again, on the left hand side, if you see, there's also an ingestion from hot storage, I mean historical data, and cold storage. Now this is a batch processing. Now there are pre-built connectors. If you just see here, there are pre-built connectors which again pushes data to the same place, which goes to the data lake. So the top part, if you see, is the streaming layer. The bottom part that you see is the batch layer, both of which finally ends up the data lake. So again, what I wanted to show is any organization, as I told, cannot run on only streaming data or on only batch mode. It always have to a combination of that. The bottom line is when we move to streaming data or real-time insights, only when our use case forces us to. Because after coming to the data lake or a data warehouse, you see there is a consumption layer, and according to consumption layer, we decide whether we need real-time streaming or not. If the user wants the data real-time, wants the insights real-time, we go for real-time. If the user is okay, or the use case is once in a day, you don't normally need to go for real-time. You can survive with the batch mode. Now one other aspect of making a pipeline, and I've just picked up something which is actually, people miss it out when they go to production. Very, very important for production is point of failure. When you create a data pipeline and you're moving to production, you always have to see in your pipeline, where is this architecture or where a module within an architecture can fail if one component of it fails. Now, if you see the first, that means the left-hand side of it, this is nothing. This is a database. You have a web UI which fetches data from this database and shows it to the user. Nothing fancy. Maybe a system which shows you your ticket booking when you put your PNR. Nothing else. What happens is, this is a single point of failure, because if the database, again, it's a database is a database, it's not God. So if it fails due to some reason, the UI loses connection with the database and there is no data that is shown to the user. So user sees a failure on the screen. In the same way, the web server, which is hosting the UI, fails. The user sees a blank screen. User is not able to interact with the system. So production, we should take care of this. And if you see on the right-hand side, what you have is, on the database side, you have 2 or 3 databases which runs on parallel, and all of these have streaming replication. That means if the data is pushed on the first database, immediately it is streamed, a copy of it is streamed to the other 2 databases, so that all 3 databases holds the same data and are consistent at any given point of time. You put a load balancer on top. When a hit comes from the web server, it goes to And there are various techniques which I'll not go into. It can be round robin, it can be load based. So it goes to any database using the protocol. But if a particular database is down, the operation doesn't fail. It moves to the other replica, which is other two replica, which is present. So the user doesn't see any failure. In the same way, on the web server, you have two web servers hosted and there's a load balancer. Again, load balancer, if you use a load balancer, you don't have to specifically say which web server or which database you want to hit. The load balancer, according to the decided protocol, takes care of it. So if web server 1 is down, it automatically goes to web server 2 and the user never sees a failure. Very, very underrated stuff, but highly important when you are going for a production pipeline and you want to make it this whole word robust, that very conveniently we put it on slides and while making our pipelines. If you go into the essence of it, this is what it is. So you just have to make it failure proof. One other part is, so I'm just picking up points which are normally creating hype in the market, and people need to understand what exactly it is. So it is server versus serverless, mostly used by players in the market like AWS, GCP, and those kinds. Again, serverless doesn't mean the code is running on air. It doesn't mean that it is running without service. It is running on somebody else's server. That's it. So if AWS is giving you something serverless, that means AWS is running on its own server. Good for you, because you don't have to take care of the server. Nothing bad in that. But the essence is it does not run on air. It runs on some server. May not be your server. So there are essentially four types that we use. One is bare metal when we talk about infra. Bare metal, physical machines, those rack space kind of stuff where we go place our order for an application server or for a database. They make the physical servers, ship it to you, that kind of stuff. Virtual machine, if you use VMware, Oracle VirtualBox on a physical server, you use a hypervisor and then you start multiple machines in that. There are containers. If you use a lot of virtual containers that have come out, Docker is one of those. And the last one is the serverless. Again, if you see the boot time, yes. If you are looking for a physical server, it is the highest. And if you are looking for serverless, it's the lowest. So the boot time is quite less. When I say boot time, it's the starting time for the server. It's very less on serverless. The app deployment lifecycle, again, when you go to server, it may take weeks. And it used to happen 20, 30 years down the line, it used to happen. So virtual machines, again, it is lesser. And when you move towards serverless, it is because they have given an abstraction, they have given you a beautiful UI, you just put your application in press, and AWS does everything for you. So it's in milliseconds. Deployment complexity, again, as you move from bare metal to serverless, your job to handle the application becomes lesser and lesser. On the bare metal, you have hardware, OS, environment, and the application code that you have to deploy. Again, when you move towards serverless, AWS takes care of everything. You just have to push your application code. Everything else is provided as service from AWS, GCP, or all these cloud players. Investment, again, when you go for physical servers, you rent dedicated servers, you have to invest on it. Same for the VM, you have to invest on it. But if you go for serverless, again, you pay for only the resources that you use. So these are some of, and again, this whole stuff is available online. You can go through it, but this is essentially what it is. Again, there are advantages and disadvantages. So this is on the left-hand side. If you see, just a quick overview of an AWS architecture. So if you see, there's nothing fancy about it. There's a web server. 15 years down the line also, there will be a web server. 15 years in the past also, there was a web server. Again, you have Kinesis, which is of the same family that I talked about, Kafka. It streams data. You have Lambda. Lambda is nothing but function as a service. So whatever code you used to write on Java or Python, you can use the same code on Lambda. It runs it as a function. S3 is nothing but a storage unit for AWS. So this all the whole crux of it is these are all provided to you as a service. You don't have to spin up any server. You don't have to take care of any server. No load balancing, no load testing. You can just use all of these components as a service without maintaining a server and build your whole data pipeline. Now, again, advantages, as I told, there is no server management required. The cost that you pay is only for the stuff that you use. It is scalable, quick deployment because you just have to push your application code. AWS does, or GCP does, or Azure does everything for you. And code can run closer to end user because you have different regions, or the CDN, and I'll not go into CDN, or do you have different regions where you can deploy codes? So it can be run closer to whatever user you're using it for. Some of the disadvantages, still there are concerns about security when we talk about cloud. It will always be because you are pushing your data to somebody else's server. So that concern is there. Not built for long running processes, because if you're running something for 24 hours and you pay for what you use, normally in a month you see that you could have purchased a server and by now you could have taken out the cost and run it for free hereafter. So again, it's built for stuff that you just run, take out the output and finish it off. So you actually pay for what you use. But if you're going to run it 24/7, you can look at other options, getting a physical server maybe. There's a dependency on vendor. Yes, if you use services from AWS, build your whole data pipeline on AWS, yes, you are dependent on them, just like Netflix is. There's a performance degrade for less used application. Yes. So these are cloud providers using a caching mechanism. So if something is very less used, yes, you will have delays there. So there may be performance degrades. So these are some of the disadvantages. Mostly the biggest disadvantages, two part. One is getting tied up with a partner. Leaving it behind is a huge challenge. Or shifting from there. Number two is not built for long process. If you're running something 24/7, better to look at other alternatives because you're going to pay a bomb on that.
Yeah, Bijoy, I don't want to interrupt because I'm thoroughly enjoying the architecture and the things which you're mentioning. Just as a time check, we have just 10 minutes.
Okay.
So if we can wind up in another minute or two so that we can take up some of the questions which are coming up.
Yes. I'm just left with the last slide. So only few points. If people looking for being a data engineer or want to start as a data engineer, there are certain things that you need to look at. The first very important thing is a strong foundation in data structure and algorithms. Just breaking it out, you need to understand what data structure you are using, arrays, linked list, pointers, all the stuff. You need to be very clear on that. SQL and data understanding. SQL is very underrated, but believe me, that's the most important thing you will need. Either you want to be a data engineer or a data scientist, doesn't matter. SQL is there and it's going to be there. Understanding data pipeline techniques, what we were talking about for last 40 minutes or so. Look at that. Now, next 2 points. Some people may disagree. I'm a programmer, or I'm a data scientist. Why should I look at network infrastructure? Believe me, this term full stack, just understanding the UI or the data massaging or building a model doesn't make you a full stack. You're a full stack only when you understand on which kind of storage you need to store your data to get the maximum throughput. You need to understand the networking requirement of pushing data from one system to other system, what kind of bandwidth you need. Without that, you may be a handicapped data engineer or a handicapped data scientist, if I say so. You'll always be dependent on network people, Linux people, infra people. So next time you look at full stack, please look at also from this perspective. And again, object-oriented programming may be a good way to start with if you're looking for transforming data, crunching data, or looking at data engineering as a whole. So that's about it. We're open for questions, if any.
Thank you, Bijoy. Thank you, Hindol, for the wonderful insights. Even I was actually looking into what are the basics of data engineering, the plumbing. The Hindol mentioned the plumbing piece, which is a very interesting piece around all the data engineering, looking into creating the right set of plumbing. I think that was a great example which was given. We learned about the producer consumer and the data characteristics. We also learned about the data engineering, the data producer. Uh, how do we ensure that we have the right data quality coming in? Also, the hot storage, the cold storage was one interesting concept. Uh, from a real-time streaming perspective, I learned more. Thank you so much, Bijoy, talking about this Kafka and Spark and how giving these use cases, how do they actually connect with each other? So, very insightful session. I'll just move into the questions which have come. One of the questions which I think would be a very common question to all of you, which is around the overall analytics services, the smart analytics which comes in, and specifically talking about the tectonic shift which has happened uh, because of specific, whether it's around the technology, whether it's around the different big data aspects which come in, the infrastructures. So what are the changes you have seen basis the pre-COVID and the post-COVID scenarios? And how does that look like, the changing face of data and analytics services?
Let me try to take a stab at that question.
Yeah.
So, of course, one thing that COVID has done is COVID has reinstated the importance of the digital strategy across pretty much all sectors. And the digital strategy essentially means more of what we were talking about, getting the right data for various use cases. For example, the loads on all of these systems, the apps and the websites have gone up significantly. The amount of processing, therefore, that is needed is going up. So the importance of data engineering and some of the robustness that Bijoy was talking about, like high availability, etc., possibly are becoming more important with COVID. For example, for a simple thing like even a app of a, if the app of a say food delivery company used to experience certain number of hits earlier, now possibly post COVID it has increased 10 times. So how do we make our data pipelines more robust? That has definitely become one important aspect. And of course, from a data science perspective, one of our key assumption is that the future is going to be like the past. So we look at past data, use the past data to build models, to build rules, and apply them on future data. Now, this whole assumption may have broken to some extent because of COVID. So all of our models, all of our rules possibly are getting rebuilt in most organizations. And again, because of this rebuilding, now we are talking about building these models very quickly because things have changed. Organizations want to rebuild all their models and rules very fast. Again, therefore, there are a lot of consumers of data who are now also taking data on batch. For example, if you have 10 models which were there and all 10 models have to be rebuilt within the next 2 months, there's a huge requirement of batch processing as well. So see, data engineering is like the bedrock. But the usage, it has changed in two ways. One is the increase in the demand for systems being more robust, and two, a lot of things being redone because the past presents the future assumption may have changed post-COVID.
Fantastic. Uh, Connecting to that, I don't know if it is a connecting question or more of so there is a question around this graph data platform and how does it actually connect with the wider ecosystem of data engineering ecosystem. I don't know, Hindol or maybe Bijoy, this is a question for you for the audience here.
Yeah, Bijoy, go ahead.
Yeah. Again, graph data. If you look at what is the use case for a graph database. So again, if I see a very usual use case where you want to connect different nodes. When I say nodes within your organization or within your customer data, I'll actually take an example of Facebook. If you see Facebook, you have friends. Friends are connected to friends. And again, if you see, there are dots that are connected, and every node is connected to each other, and you don't know, these are infinite. So when you have that kind of use case, where you have that kind of connection, is when you go for graph database, which helps you process those connections actually, give you insights on those connections. Now if individual customers where you don't have connections between one customer to another, and these are just set of individual customers. So if you are trying to use a graph database in that case, it's an overkill. Actually, it doesn't give you anything. It's just like a normal NoSQL. So unless you have a use case where your data is again connected to each other, you have various suppliers connected to each other, various customers connected to each other. You want to look at relationships. That kind of insights when you use or need is when you go for graph platforms. So I think right now in India, at least, there are not many such use cases which really compels you for using a graph. So maybe an overhyped stuff right now.
Okay, great. Thank you, Bijoy. The last question in 3 minutes. So, which says, what is a streaming dashboard and its role in data architecture?
Okay. So I know in one of our slides it was written maybe in that Actify platform architecture streaming dashboard. That's normally a dashboard which shows you real-time insights, and I'll give you example. Suppose for a manufacturing company, a manufacturing industry, somebody wants a dashboard where they can see if any heavy machine or if any machines work which have sensors goes down. So they want a real-time alert or a real-time mark on the dashboard whenever it goes down. So when the data streams from the sensor real-time, the dashboard should have the capability and right from the real data getting generated from the source, your processing system, which is able to process it real-time, and the dashboard able to show the user real-time a pop-up that machine number 2 has a problem, it has stopped working. So needs immediate attention. So this kind of use case when you look at, that's what we meant by streaming dashboard. Mostly it is streaming or real-time alert. And its role in the data architecture, again, if you are looking at this kind of alert, real-time alerts, your data and your data processing needs something that can process this high velocity data, something like Kafka or Spark, a combination of Kafka and Spark.
Great. Thank you, Bijoy. I think we are on the top of the hour, so I'll just thank you so much, Hindol and Bijoy, for this wonderful session. At least I learned a few things around data engineering, specifically from a use case perspective, in terms of how the different technologies connect, what are the key trends which are happening, and specifically, what does that mean from if you want to make your career in data engineering? Thank you so much for spending time this Sunday and giving us these wonderful insights. Thank you so much to the
Thank you.
audience for sticking for the for 1 hour and actually listening to these insights. I hope you have a great rest of the Sunday, and thank you so much again. Enjoy your Sunday. Happy Sunday.
Thank you.
Thank you.
Thank you. Thank you.